This is Module 11, Lesson 2. We are going to talk about electromagnetic induction right now. We've already looked at what makes something magnetic. Let's look at some things that we can actually do with that. So what electromagnetism is, as you might guess, is of course electricity and magnetism together. A fellow by the last name of Oersted discovered that if you move a current, it makes a magnetic field. So, and that's an important concept right there, is that the current has to be moving. So if you have a static charge, that means it doesn't move. It's just like a point charge like we did in the previous module, and it doesn't go anywhere. It does not make a magnetic field. But if we take that charge, whether it's positive or negative, and we move it, we get a magnet. So what he discovered was that if you take a current, you see the current right here, it's in red, and we run it through this wire in the direction of the arrow, what happens is that it creates a magnet and the fields actually go around it in circles. Now, a couple of things about the fields. They are perpendicular to the wire. That's what the purpose of this is to show you, like in a plane, they are perpendicular to this particular wire, and they do go in circles. Now, how you figure out the direction that the current is going or that the field lines are going is using this thing called the right-hand rule, and it's the first right-hand rule. There's actually 3 right-hand rules. We are going to focus on the first one. And what the right-hand rule says is that you curl your fingers around the wire in the direction of the current. So notice this person's fingers are curling around in this direction where my arrow is pointing. Where your fingernails point is the direction that the magnetic field is going. And if you do that, your thumb will be pointing in the direction that the current is going. Or you could use this in reverse. If you point your thumb the way that you know that the current is going, then your fingers, where your fingernails are pointing, will tell you which way the current, or the magnetic field is going. If you reverse the current, so if we took the current, and I'll do it in a different color other than red, do it in green. If we took the current and we made it go this direction, you would have to take your hand and flip it over, if it makes sense, so that you're looking at the top of it instead of the palm, so that your thumb is pointing down this direction. So I don't really know how to draw that person's thumb going this way, and their fingers would be curling over it like this, so that you're looking at the top of their hand that way. Like you would be looking at their fingers up on top, and that way you know that the field is now going the other direction around it. Instead of coming up and over, it would be going over and down, and then their thumb would be pointing in the opposite direction. This is a lot easier if you hold your hand up in the air and do this than me trying to draw someone's ugly green hand. Now, what if we make a loop out of the wire? For this particular one right here, this is for a straight wire. So if we have a straight wire, you do need to know the direction that the fields will go, how to figure it out, and that they're perpendicular to the wire itself. So what if we take the straight wire and we wrap it into a loop? You know, so if you see this, like here's the straight wire, we've wrapped it into a loop, and we run a current through it. And that's what it says, is we know that a current carrying wire, so a current moving through a wire makes a magnetic field. What if we loop it? Well, if we loop it, what happens is this. We still get circles. So I'm going to do this in green and hope that it doesn't make too much of an ugly mess here. But what we know is that around this wire, we're going to have these magnetic fields that loop around in circles all over this particular wire. We know that they're perpendicular at every angle. You know, they're making a perpendicular field line all around this particular loop. What that does is it concentrates it so that we end up with basically this pattern to our fields. Let me switch back to this. That's not giving me my pen. Now, there we go. Okay. So what we end up with is this. We end up with, you know, distinct circles, and then we end up with this massive concentration of fields that's going through the center. If you loop multiple loops together, like this has 1, 2, 3, 4 coils together, what we end up with is we end up with circles going around the outside. You see those circles up here? Like the circle here, a circle here, a circle here, a circle here. We got circles at the bottom. And then we end up with this path straight through it being created by the current. It resembles a bar magnet. Remember when we drew the bar magnet? Let's see if I can change over to a highlighter. Like if we had a bar magnet right here in the middle, where I'm highlighting, this resembles the currents, or not the currents, but the magnetic fields that you would have from a bar magnet. So if this up here would be my north, and this would be my south, and notice it's coming out of the north and it's wrapping itself around and coming back in, it most closely resembles the field lines of a giant bar magnet. Okay? So what can we do with this? If we do this, if we wrap them together, we make something called a solenoid. A solenoid is just a fancy electromagnet. There are several things that you can do to increase the strength of a solenoid. You can increase your number of turns of wire. So like this one has 4. If we increased it and we made it more, like this, then that would make a stronger solenoid. If we added an iron core, if we took a piece of iron and we put it down the inside of this, like an iron rod, and put it in the middle here, and then wrapped the coil around it, that would make it even stronger. Or if we increase the current that's going through the wire, so over here, if you can picture coming through this wire, we have 6 volts that are going through it and coming out on the other end, and we change that out for 12 volts. And that would make it an even stronger electromagnet if we increase the current, because if we increase the voltage, we're going to increase the current. And then I told you again that the magnetic fields are most like a bar magnet. Here's another example of this. This is a better picture of doing this. We can also change this around. And we know that if we have a moving charge, we create a magnetic field. Well, if we move a magnet inside of a coil, like no electricity is involved this time, we actually generate electricity. So this works both ways. Faraday actually discovered this. I'll put his name here. Faraday discovered the opposite. Oersted discovered that moving current makes a magnet. Faraday discovered that moving magnets create a current. So if we take this magnet and we push it inside of this coil, we get a current. In this particular case, it heads to the left. And if we pull the bar magnet back out, we still create a current, but this time the current goes to the right. So we can change the direction of the magnetic field by moving the current, or we can change the direction of the current by moving the magnetic field. All right, let's talk about this real quick because it'll lead us into our next lesson, which is about motors and generators. We already know that if we have a current carrying wire, we get a magnetic force. We know that current moving in a wire makes a magnetic field and also makes a magnetic force. Magnetic force is the idea of pushing and pulling things. And it says right here, imagine a current carrying wire being placed between 2 permanent magnets. Okay, we're going to focus right now on the 2 little rectangles down here. These are going to be our permanent magnets. And so, let's see, I have to think this through before I do this if I want them to match up with the words on the screen. They're going to be going the same direction. So as I'm doing the right-hand rule here as I'm recording this, trying to figure out like which way I want things to go. So I want them to go that way. Okay, so we're going to make this south and this north, and this south and this north. So we have 2 magnets that are together, okay? They are attracting to each other. So what we know is going to happen is we know that we are going to get field lines, if we draw this from our previous lesson, that go from north to south of these 2 big magnets that we have, okay? So I'm just focusing on the fields between these 2. All right, the circle in the middle is a wire, and I want you to picture a straight wire like we had at the beginning of this. So if we have a straight wire and we are going to put a current through this particular wire, okay, I want you to picture on this that the current, come on now, is coming out of the screen at you. Like it is coming straight out of your computer or your phone or your tablet screen, and it's heading straight for your face where you're watching this. So we are putting the current coming out of the computer. If you use the right-hand rule and you make a fist out of your hand, and no, let's see. We gotta forget that this is the right hand. So no, actually I need it to go into the computer screen. See, this is difficult. It does bring up a valid point that, like if you use your left hand, you're going to change the direction of the current. So using your right hand, it's actually going to go into the computer screen. So we are going to take our right hand and we are going to make a fist out of it, and we are going to do it so that our thumb, if you stick it out, will point into the computer screen. And in that particular case, your fingers are going to be curled over the top. What that means is that the magnetic field coming out of this wire is going to be heading in this direction. Well, I want you to notice something. On top, that means that they are going in the same direction. They are heading to the right, as it comes up and over. So what that means is that they are going to repel. Why would that be? Because their magnetic fields are going to be going in the same direction. They are not going to like that. Okay, and on the bottom, they're going to be pointing in opposite directions, because on the bottom of this curve, they're headed to the left, but the field lines here on our green line are going to the right. They are opposites, which means that they will attract. So what does this have to do with anything? It means that we are creating a movement here, and if we took the shape of something else, like perhaps if we had something that was shaped differently, it would push it to the right on the top and it would be pushing it to the left on the bottom. And what this does is it introduces the idea of spin. It would let us spin something between these two green magnets that we have going on right here. Okay, and it gets us to the idea of motors and generators, which is coming up next. Something else that has to do with that has to also do with what we're talking about here, is talking about the magnetic force. If we have an object like this that's spinning inside of a magnetic field and we run a current through this particular wire, so pretend that this little kind of mustardy, yellowy colored thing here is spinning. So put it on a point right here and pretend like we're spinning it around. If we run a current through it, what's going to happen is our magnetic force is going to be the largest whenever it is perpendicular to the magnetic field. It's because of what we just talked about. Because remember, if this has field lines that are coming up and over it, or let's say the current in this case is going this way, it's actually going to be going the other way. I didn't look at the current right there. So if the current is coming at us, let's fix this. The current right here, it says, is traveling like down, like towards us, down this particular wire. Then, again, take your right hand, point your thumb at yourself and make your little fist like you're supposed to. It means our fields are going to be going up and over the top. They are going to interact the most whenever this wire is perpendicular to the magnetic field. Whenever you put it at an angle, they're kind of interacting, but not as much. And whenever you put it parallel, they're not interacting at all. So whenever you have your current moving parallel to the magnetic field, you actually get zero magnetic force, and you get the maximum force whenever it's perpendicular to it. Okay, so that's the end of this lesson. What are you supposed to do with this? You're supposed to rewatch it until you can kind of explain some of these things and see if all of this confusing magnetic field stuff makes any sense. I do not have any particular practice problems for you on this. It's mainly just a matter of, can you explain these things? So you can go back through it and try to answer some of the questions that I'm asking you. That'd be a way to practice. Work on memorizing the definitions and be ready to just make sure all of this stuff is in your brain.